Hello and welcome to Oceanography. I am Mike Phillips, the instructor for this course. This is my contact information, and we will go over this more in class, and it's also available online. So the first chapter that we're going to discuss is Chapter 1. It's an ocean world, and I'm just going to use these slides to highlight a few important points. You should absolutely read the entire chapter, and this goes throughout the semester. These narrated PowerPoints will just be to highlight some things that I think are especially important and to help you as you answer questions for the exam, but to get a complete understanding and to do well in the course, you really do need to read the chapters in the textbook and attend our regular weekly sessions of the class. So like I said, this is just kind of an overview thing to highlight some important points. So first of all, oceanography, we're studying and discussing the world ocean. And one of the things to understand about this textbook and the approach is that while very often we think of, hey, there are four oceans, the Atlantic, Pacific, Arctic, and Indian Ocean, really one of the things you're going to learn this semester is that it's all one ocean, that the water circulates between all the ocean basins. For convenience, we divide things up between the different basins and they're separated by the continents, but really it operates as one ocean. 97% of the Earth's water is found in the oceans. This water is saline, which means that it has a significant amount of dissolved material in it. In fact, one of the things that we'll find out in the chapter on ocean chemistry is that the salinity of the ocean is around 3.4 to 3.5%. So 3.4 to 3.5% of the water in the ocean is actually dissolved substances. Sodium and chloride are the most notable, but we'll find out that there's actually a lot more dissolved in seawater. The ocean covers 139 million square miles, which ends up being about 3/4 of the Earth's surface. It has an average depth of 12,451 feet, which is a little bit more than 2 miles. So the ocean is on average about 2 miles deep. The maximum depth of the ocean, 36,000 feet, would be about 7 miles deep, and that's the Challenger Deep. And we'll find deep places around the ocean as well as some very shallow places as well. The total volume is 329 million cubic miles. That's just a huge number. It's hard to comprehend. One little interesting fact I like to include is that the tallest mountain on the ocean floor is the Big Island of Hawaii. If you drained all the water out of the ocean basin, the Big Island of Hawaii would be basically a giant mountain sitting on the ocean floor. And you can see it's about 33,000 feet tall. About 10 or 15,000 of that is underwater. So about half of that is underwater. This class is a science class. So we want to spend a little bit of time talking about science and how it works. Science is a systematic process. We do our best to be objective, so to take ourselves kind of out of the equation, and it's not about how we feel about things, it's about what we observe and what we know and can test and can see has actually happened. It's very important in the sciences to share your results so that other people can check your work, but also so that they can build on what you have done. One of the important aspects of science is making sure that you are very clear about your level of certainty. So how certain are we that the information, for example, in the textbook is true? For an introductory level textbook, the level of certainty of information in here is quite high. So the information you find in the textbook has been researched and studied and examined and critiqued for many, many, many years. And so this is some pretty solid stuff. If you were to take upper level courses in oceanography or graduate level courses in oceanography or do research in oceanography, you would start to work in areas where the level of certainty is lower, that you're trying to figure out what's going on, and you need to have an idea of how certain you are or how uncertain you are. If there's a lot of uncertainty, that just means a lot more work needs to be done. And of course, that leads us to the last point here, which is that um, it's very important in the sciences to be open to criticism and revision. One of the reasons why we share our results is so that other people can look at them and give us feedback and try to repeat the work that we've done, see if it makes sense based on the research they've done. So criticism and revision is extremely important in the sciences to make sure that we have the best possible answer with the highest level of certainty. So to be a little more specific, this is something that a lot of people are familiar with, and we'll talk about this in greater detail in class. But this is kind of an overview of how science works. We begin by making observations, and scientists are by nature very curious people. People in general are curious, and science as a profession or as a realm of study kind of springs from this observation and questioning that people just generally do. They see something, they want to know why, they want to know what's going on. So the scientific process is just kind of an orderly approach to investigation. We typically start by coming up with a sort of a research question, and we follow that up with working explanations. Now, we call these hypotheses. A hypothesis, that level of the investigation, just indicates we don't have a lot of data to support our conclusions. It makes sense in the context of other work that other people have done, in the context of the data that we already have, but we understand that it's kind of a working explanation. If possible, we like to have more than one hypothesis to work on, especially early on in the process, because it broadens our investigation and it helps ensure that we're investigating kind of all aspects. It also means that we're not very strongly tied into our initial explanation, that we have several of them. So if in the course of our investigation something turns out not to work, it's a little easier to set it aside if we have other explanations that we're working on at the same time. And so that's what moves us into the investigation phase. And again, the investigation in some ways is directed by what our hypotheses are, because really what we're trying to do is prove our hypotheses wrong. It turns out, if you look at this from a philosophical and a logical standpoint, it's very hard to prove something's correct, because you can never investigate 100% of all aspects of the issue that you're investigating. On the other hand, you can pick out certain aspects and say, if I find this out, I can prove this wrong. So you start trying to prove yourself wrong, and the more often you fail, so the more often the hypothesis actually is like, you know what, hey, it passed that test, it becomes a stronger, more well-supported hypothesis. So investigations very often involve looking for evidence to prove a hypothesis wrong, and when you can't prove it wrong, it just gives more support for the fact that it's probably correct. So that's where revision and negation come in. You take the results of your investigation and you look at your hypotheses and say, which ones are the strongest, which ones don't work, and you do revisions, and you probably are going to end up doing some more investigation after that. Ultimately, what we're going for is what we would call the best explanation, which would end up being our theory. If it's got a lot of support, a preponderance of evidence, 85, 95% certainty, we might be comfortable calling it a theory. And that's really the best that we can hope for. That's what we're going for, is this very strongly supported idea that we can call a theory. We recognize that even if it's very clear that this is what's going on, that we can probably make some adjustments around the edges and make it even better in the future. And so that's why we hang on to this term theory. And at the end of all this, and during the process very often, we publish. So publication is just a general term that we use for sharing that information with others. It could be that you give a talk at a conference. It could be that you write an article for a journal. It could be that you write a textbook. And all those are part of the scientific process. Some things that we try to keep in mind is that our scientific explanations really must be natural. We're looking for natural cause and natural occurrences. We don't bring in special causes because we can't find any other explanation. If we can't find a natural cause, we just keep looking. We have to support it with the available data. We have to be able to test and falsify. We have to be willing to revise and refine or throw it out. And we recognize that it also should be predictive. So once we come up with a really strong explanation, we should be able to use that to kind of predict future findings. That's a really good way to test your hypothesis and see if it holds up. As we're working through this, we find that we use several kinds of data, and we put our data really into two broad categories. We have qualitative data, which is just descriptive data. It's words, sketches, descriptions. And then we have the quantitative data, which is numerical measurements, and it's conveyed with numbers. A lot of people are much more comfortable with the quantitative data. They feel like that's what science is all about, but it is absolutely not. And there's a lot of information that we're going to convey in this course that is qualitative data. And qualitative data is very useful and very important in the sciences. It is not strictly everything tied to numbers. So, what about oceanography? Well, oceanography is marine science. It is the study of the ocean and kind of every aspect of it. And what you'll see as you look through the textbook and throughout the semester is that we are going to tap into many other scientific realms and use those as we study the ocean. Geology is the study of the earth, so you'll find I am a geologist, so this is kind of my area of expertise, but you'll find many of the chapters deal with the physical earth. So we'll be talking about plate tectonics and the formation of ocean basins. We'll be talking about processes that act along the coast. Those are all from the science of geology. We'll see, we talk about the chemistry and the physics of seawater, very important aspects of oceanography. And at the end of the semester, we're going to talk about life in the ocean, so marine biology, and that's another aspect of oceanography. Here at the beginning of the semester, we'll talk a little bit about the history of marine science and a little bit about archaeology that occurs in the ocean. And we'll be talking about geography, like how we find our way around. And I would encourage you to take a look at a lot of the maps and charts in the book so that you understand where we are and what we're speaking of. And so oceanography is kind of a fun topic because it touches on so many different aspects of science. And this is the first of two parts of the next set of narrated slides. We'll talk about the origin of the ocean's water and our planet.